Great. Hi, everyone. Welcome to the final presentation in our Databricks lecture series. I'm really glad that you could all join us. I'm Drew Pollan. I'm the academic director of the MIDS program here at the iSchool. I'm very pleased to introduce Jules Damji, who is leading our session today. He'll be exploring some of the challenges of data at scale, looking at MLflow and Delta Lake, and we'll discuss how machine learning at scale facilitates the future of data science. Jules is a developer advocate at Databricks and an MLflow contributor. He's a hands-on developer with over 15 years of experience and has worked at leading companies such as Sun Microsystems, Netscape at Home, Opsware and LabCloud, VeriSign, ProQuest, and Hortonworks, building large-scale distributed systems. He holds bachelor's and master's degrees in computer science from Oregon State University and Cal State Chico, and a master's in political advocacy and communication from Johns Hopkins University. So before we get started, I just want everybody to know that we're going to set aside 10 minutes or so at the end of the presentation for questions. So feel free to pose questions in the Q&A panel. You can see it in the bottom there in the tool bar, or in the chat, and we'll be sure to return to them at the end of the session. Jules, welcome. Thank you so much for joining us today.
Well, thank you very much, Drew, for the kind introduction, and thanks a lot for this invite. It's really an honor to be here at Berkeley. Berkeley has a very strong emotional ties for me. I started my first computer science courses a very long time ago, and I'm not going to date myself, but I started working, taking some summer courses in Pascal and Fortran. If I say Fortran, that pretty much dates me quite a bit. In Corey Hall, working midnight and late hours there. So coming back to Berkeley and being associated with Berkeley is actually really an honor. And both my children graduated from UC Berkeley. So it is a very special place for me. And I want to thank you guys for inviting me. So delighted to be here. What I want to do today is really talk about whenever we have a future, and that's why I have a question mark in my title. Whenever you talk about future, you're always worried about expected to look into the crystal ball. So I had to tread very carefully to talk about what are some of the things that I'm going to talk about today, and I want to frame this particular presentation in a number of ways. But I'd like to start first by saying this has really been a year of hope in more ways than one. You know, it has been a year where we actually seen the experience, the accelerated adoption of certain data technologies. We have come to see that data has actually a center of everything, where data is pulling a lot of data teams together. We have actually even acknowledged the interplay of data teams. And when I talk about data teams, I'm talking about data scientists, machine learning engineers, data analysts, and all the people who actually work with data to actually come together. And so what I like to do is frame the discussion today in how data has become the center of gravity. Now, you've probably heard the old cliche saying, you know, data is a new oil, but I like to sort of rephrase it differently. Is data is really the new center of gravity. And having said that, I want to sort of frame today's discourse in discussing what are some of the data problems that have sort of emerged recently because of the scale and the type of data we deal with, and how it actually impedes us to do advanced analytics. And I'm using the term advanced analytics over here in the sense that it encompasses all kinds of advanced analytics that you do with large data, whether you're doing data analysis, where you're looking at the historical data to do some sort of what happened, or where you're trying to do a forecasting with the data, or you're trying to predict what the future is going to be, whether you're doing machine learning or whether you're doing deep learning. So advanced analytics sort of is an umbrella term to include all kinds of analytics. And what are some of the problems that existed in the past? What were some of the data architectures that impeded us to do today? And what is the new future looking like, especially now that you probably have heard this term called lakehouse, which is a new paradigm that has forced us to look into data and data architectures in a different way. And in particular, I'm going to frame the discussion how two open source technology fit into the grand scheme of things in this particular new paradigm called lakehouse. Now, for those of you who don't know Databricks, it's a company that I work for, and for all of our founders have very strong academic and historical ties with UC Berkeley. So Berkeley actually is a center of everything. A lot of graduates who from the EECS actually come and work for us as well. So it's a pleasure to be part of it. And we provide a cloud analytic platform for data teams to actually work together. And this includes data engineers, data scientists, ML engineers, and data analysts. And as you know, Apache Spark was founded at AmpLab, which is now called Rice Lab. And so we actually provide that as a managed service along with other open source projects such as MLflow and Delta Lake, which are now provided as part of the unified platform. And we have close to over 7,000 customers across the globe who are using this analytics platform. Having said that, what are the challenges today? Why is it that big data is so difficult today? And how do you actually grapple with data beyond 2020? When you look at yourself in the mirror, metaphorically speaking, you look at all the sea of data, how do you actually grapple with? And I think there are a few things that actually have emerged over a period of time. One is the data quality, and other one is the tardiness, right? It's very important to have good data quality for doing good data science and good insights and building a scalable machine level. And then staleness is another important thing, that we actually want data to be in real time, meaning data not to be stale. And obviously volume and scale is now something that we actually have to deal on a daily basis. And if you look at some of the problems that data analysts and data professionals have complained about, a recent survey that actually showed that about 60% of the people who are dealing with advanced analytics always report that they're dealing with bad data because they have to do a lot of cleaning data 60% of the time. A good number of them have also reported that the data becomes very stale. And sometimes when they do forecasting or when they do real-time analysis, they're dealing with data which is about 2 months old, which is not a very good thing to do because you really don't get very accurate results when you're building machine learning models. And majority of them saying that data comes sometimes from unreliable sources, and after about 12 months, that data is completely meaningless. So what do you do with that? And I think a similar sentiment was also echoed by a Kaggle data science survey, which, as you guys know, that we spend a fair amount of time analyzing and understanding data. And if the data is bad, if the data is old, then you're not really getting a very accurate picture of that. And the good amount of time is also spent in maintaining these infrastructures that we actually have in order to build an existing pipeline so you can actually get good data, you can get quality data, you can scale the data, and all these are sort of important part of it. So what seems to be the problem? Why is it so difficult to get high quality data in a timely manner? And I think part is because the problem is of our own making, and because we are stuck in the old ways, right? We want to feel comfortable in the systems and the architectures and the languages that we have built, and we want to continue using that. And I think the other problem is that data evolves. We have seen that data evolves, and we have to evolve with it. And when I talk about I'm talking about the data architectures have to evolve. So in order for us to understand how data architectures have evolved over a period of time, to grapple some of the data that has actually changed with it over the past 2 or 3 decades, let's just take a quick peek at the history of how data architectures have evolved and how people did advanced analytics from the early years of 1980s to today. So if you look at the architecture of the 1980s, data warehouses were the cafe lattes, right? They were principle, they were very popular. And one of the reasons they were popular because they were a singular architecture that allowed you to do the ETL directly from this myriad operational databases that you actually had in order for you to actually do some business analytics and SQL reports directly from the data warehouses. And they were purposely built, right? They were purposely built to perform very high performing SQL analytics in BI because they provided you structured tables. They had schemas so you can verify the data quality conformed to the schema. They had highly primary and secondary indexes, so you can actually query the data quite efficiently using the SQL operators. And the caching was also used, and all the other techniques that you normally use and expect a perform engine to perform were part of the data warehouses. And they also provided powerful management features such as ACID transactions. So you always get the reliable quality of data. When you ask for a table to come back and you perform a certain operations, such as CRUD operations, you know that it either fails or it's guaranteed that it's successful. And multiple readers and multiple writers can actually do that. And more importantly, it gave you the ability to time travel, right? So you can actually go back in time to fetch the exact amount of data that you actually need. The problem was that now machine learning data scientists really, you can't really do SQL. You can't really do machine learning on SQL because SQL is a non-Turing language. So if you want to do complicated computations, you had to extract the data out from the data warehouses to put it somewhere else, which is not really a good experience for data scientists and machine learning because it introduces time delay as well. I think what happened was that in the 80s, it served that particular purpose, right? Data houses were popular, and they're popular today. I'm not saying they're not. They are popular today. They are being used quite a bit for specific purposes. Then came the 2010s, and 2010s sort of revealed certain constraints and certain problems that data warehouses faced. And one of them was that because of the data changed, as you guys can remember, 2010 was, you had the explosion of the internet. You had unstructured data and semi-structured data in terms of JSON and XML and YAML files. You had time series data that you actually had to do forecasting on. You had logs from all the devices and from all the servers that you actually had to analyze. You had digital images that had to be transcoded and documents that on which you actually want to do some sort of a language analysis or you want to do NLP, and that wasn't very suitable for data warehouses. So they couldn't afford, or they couldn't provide you the infrastructure to deal with unstructured data or semi-structured data. The other problem is because of the fact that you actually now have to deal with a massive amount of large data sets. The data warehouses tables were built to handle and optimize for small data. So now you actually have a high cost of creating multiple tables all across and expanding horizontally or vertically, depending on which way. And that actually incurred quite a bit of cost. But I think the most important factor that you have to remember as a data scientist and as doing advanced analytics, that there's no support in this particular infrastructure to be able to actually do data science and ML at scale that is asked of us today, because of the fact that people are building machine learning models on daily basis, on hourly basis, on minutes, and they're deploying it and testing with large amounts of data. So you actually need that capability. So because of these particular constraints, obviously, we being human beings, we have to evolve with the data structure. And if you actually want to keep up with the pace and time to be able to handle all these things, data architectures have to evolve with the data types. So now then came this whole notion of data lakes. You know, what are data lakes? And the whole idea behind data lake was because they were low cost storage, you could actually put your raw data or all unstructured data into a data lake. And because they actually use open source file formats like Parquet, you could pretty much store anything and everything you actually wanted in this particular low format in the data lake. So they provided you with a low cost horizontal scalability. And because of the fact that the cloud providers now separated the compute and storage, you have the ability now to put the compute engines to be very powerful, and you have the ability to actually get the data you actually want. And the other thing is that for the subset of the data you actually needed for doing some real-time analysis or data warehouses, you could take partially a subset of the data and then put it under data warehouses, or you can upload it using ETL into real-time databases that can actually do BI reports. So now you actually have all these workloads that you can actually support, right? And more importantly, because of the fact that all these machine learning libraries that you actually have today have the ability to directly read text files and CSV files and images directly from the data. And so now you actually have a low storage area. So you might ask, Jules, the problem is done. You know, what is the particular problem? And I think the problem manifested itself in a number of cases, because now you have the ability to store data in large storage across systems, but the ETL processes now have introduced a complexity, because now you actually have multiple storage systems with with different semantics. Now you have SQL for data warehouses. Now you have real-time databases where you're actually doing an ETL to generate the reports. And these can actually introduce delays, and this can introduce bugs as well. So now you actually have ETL happening in two different places. You have data preparation on the machine learning side, where you actually have to prepare the data in order for you to do your analysis and training and validation. And you also want to do ETL on the other side, where you actually want to have the ability to have data warehouses, so you can actually do BI and do some real-time reporting. So now there's extra ETL that actually introduces bugs, and if bugs happen, there's a time delay. And as a result of that, we are back to square one. Remember, I showed you about what are some of the problems that we're facing today, and data reliability is one of them. And now we're actually introducing the problem of timeliness. And these ETL processes can actually take long, right? Sometimes it can take hours to days. And so you're always getting stale data and not getting the real data. And so even though they solved this particular problem at the time when the volume wasn't growing, but today with the scale that we're dealing with and with the immediacy that we're actually dealing with machine learning, we can't really afford this extra ETL steps. And as a result of that, we are introducing a high cost, because now if you want to do continuous ETL, you are now dealing with extra engineering cost, and things can actually break, and you're actually fixing it. So you're fixing the problem in order to actually get the latest data, but you're still introducing that. So it's a slippery slope there. So what do you do, right? You're asking your question. I mean, this is the current architecture that a lot of enterprises are actually using. What is it we can actually do? And a new sort of paradigm sort of evolved. As I said earlier, that in order for us to handle the fast changing and the differing data on a daily basis, we have to be agile, we have to be adaptable. And so there is this new architecture, new vision that you might have heard about called Lakehouse vision. And it's being bandied around both in the academic world and also in the industry. And you will hear the term called Lakehouse vision. And the idea is very simple. It goes back to the early days where you actually want to have a single platform for every use case, whether you're doing streaming analytics, whether you're using BI, whether you're using data science, or you're using machine learning. You still use the data lake to store all your raw data in whatever format that you actually want. But important thing is that you build a layer on top of it, which is your management layer. And the management layer is where you actually provide the ability to get tables in a transaction in an ACID manner. You can provide versioning for tables that comprise of particular file. You can use all the high performance techniques that data warehouses provided as part of this management layer. And this now is becoming now the future, where people are saying, okay, this actually makes sense. We don't want to have the multiple ETL processes. We want to have one data layer that actually manages all the management layer features, built on top of the data lake that gives us the horizontal scale, and built on an open file format. And we provide the access directly on top of the data layer that all these other workloads can actually do that without having to wait for that. They have timely data, they have instant data right away. And this particular vision is today that most of the enterprises are beginning to adopt, and it's actually taking off because it's actually solving the data quality and data timeliness manner. And so idea is, as I said earlier, is that you use the chip storage for your data lake storage, and you put your Parquet or you put important file format in the data storage. You build the management layer that gives you the transactions, the versioning, all that as part of your meta layer. And then you provide SQL and high-level APIs that, instead of using independent way to get access to data, it goes to the management layer. So applications can actually say, okay, give me this particular table, and then it will figure out what are the best version, what's the recent version of this particular table, and provide you with the exact files that you actually need. And your subsequent respective applications can read that particular file and process it in due course. And again, the question is, can we get the state-of-the-art performance and the governance that features this particular design? In other words, can I get the best of the both worlds? That I get massive amount of horizontal storage at the same level, the ability to actually do transactions at scale, which is normally expected of enterprise or database systems that allow you to do that. And the question is, yes, I think we can actually do that. And the reason we can actually do that is because there is a confluence of these emerging technologies which are actually enabling and undergirding the vision of what data lake lakehouse is all about. And one is the meta layers which are built on top of data lakes that allow you to do transaction at scale, that provide you the versioning capability, so you can actually have multiple applications, do transactions without corrupting the data. And this is an important part of technology which is actually evolving, that is providing this particular vision to come true. And the second one is that there are SQL performance engines which are being built on top of the data lake that take advantage of the storage system that have high throughput IO performance, and they're using the file formats, the open file formats such as Parquet, which is a very efficient column database, to be able to actually build query engines on top of that. And the last but not least is, because we want to do machine learning at scale, we want to have all these frameworks that we are used to have declarative access directly to that through that money management layer. Now, let me just talk briefly about each of those three technologies that enable and undergird this vision of lakehouse, which is really taking off. And we're beginning to see a lot of noise in the industry about this new paradigm, which is actually a shift from the older one. So data lakes is good, right? A normal data lake allows you to put any number of files you actually want into the data lake. The problem is that there's no versioning. So in other words, if you might be looking at an old version of the file, or you might be looking at an old version of the table, you don't know whether somebody has just updated it or somebody actually has just deleted it, or you might get the data which is not the most current one. And the management of the meta layers on top of the data lake allows you to give you this rich management features in an ACID manner, so that you can have multiple applications, can do isolation and get the appropriate files which are part of the particular table. And it allows you to do parallel processing, so multiple clients can say, give me the version of all the files which are comprised of this particular table called V1, and I'll get the management layer will figure out exactly what are the files which are part of this particular transaction called table version 1, and then return you back those. Now, this meta layer are being developed in the open source manner across the industry. We at Databricks implement the Delta Lake, which is an open source that we donated to Linux Foundation. There's a similar meta layer for data lakes being developed and contributed to Apache called Apache Iceberg, which Netflix uses it at scale to do their transaction, to manage their data lakes. And then ACID has also been introduced in Hive 3.0 that allows you to do ACID transaction on the Hive meta store. And we actually have seen that Delta Lake is now sort of emerging and taking really industry by the storm, is because this management layer allows you, for example, to be able to have multiple clients access data in a manner that doesn't interfere with other transactions. So if you have two applications which are saying, give me the version 2 of this particular table, the transaction log exactly knows that version 2 was created at certain particular time, and it only contains file 1, file 2, and file 3. On the other hand, when you have a query that an application deletes that, it creates a version 3 of the transaction log. Now the version 3 of that particular table will only have files with the deleted entries. So either see 1 or the 2, but you never see something in between, which data lake initially didn't have that. But having this management layer, part of the data lake technology with the transaction log, allows you to do that as massive scale. The other thing that data lake allows you to do is to be able to have other management features which are expected in enterprises. So I can actually take my Delta Lake table and read it as a stream, and then merge it and do inserts and do upserts and do all the DML operations along with Kafka or any other streaming operations. So now I can actually update the data in real time. But the important thing is that now you can actually do time travel, just like you could actually do that in the data warehouses, where I can actually now go back to a particular version of the table. And this is very, very important for machine learning to do at scale, because you want to be able to reproduce a model that you created 6 months ago, right? If you were storing and reading everything from data, like you have no idea what files were used. But over here, you know exactly what files were used, you know exactly what features were used, how they were used, and that allows you to reproduce your machine learning model or your experiment if you actually wanted to do that. And then the other things they actually provided you is the ability to control and ensure that the data quality is actually maintained. Now, remember I talked about data quality in the survey, and I talked about why data quality is an important part in doing machine learning at scale. And this is one way where you can actually enforce that the new data that's coming in is conformant to a particular schema. And if the schema evolves, then you make sure that if you go back to a particular table, then the evolved schema won't have will have entries which are either null entries or some other type of entries that you can actually fulfill in it. And so this is actually an important part of the management feature for Delta Lake. And then we're beginning to see, at least within the Databricks, that our customers, 50% of their workload, IO workloads in excess of exabytes a day are using and handled by Delta Lake. And we're beginning to see the same amount of interest and adoption in the industry, where some of the major ETL vendors are using Delta Lake for ingestion. They're using Delta Lake as a storage mechanism in their cloud, and some of the popular SQL engine on the far right-hand side are actually building query connectors to extract the data and then do analysis. So we are beginning to see that this is really emerging as one of the standards in part of the Lakehouse vision. Now, having a meta layer by itself and of itself is not enough. You actually need to ensure that the query engines, which are built on top of the data lake, that take advantage of the storage system, and file formats scale as well, and they are performant in the same manner that the data warehouses were. And so let's look at that in particular detail. We have seen that some of the Lakehouse engines which are being developed today sort of directly take advantage of some of the techniques that we all are familiar with. If you're actually building distributed system, or if you're building very high efficient access system, caching is an important element of it. And so all the hot data that you actually read from the data can be actually cached using the recent RAM technology, or you can actually store them in highly available SSD drives. And possibly if you're dealing with images, or if you're dealing with recordings or voice, those could be sort of possibly transcoded as well. You can also use some of the techniques that people actually use today, where even though you don't have the control over the file format, because file format is Parquet, but you can control how you actually lay out the structure of data. You cluster co-access data together, you sort them out, you partition them out, you use reorder to access them, and this gives you a lot of performance. So for using caching techniques, it actually matches some of the data warehouses on hot data. And then these other techniques that you can actually attach, say, auxiliary data structure like statistics and indexes. So when you make a particular query, such as a column for date, you know that a certain range of dates will only appear in this particular file. So you only go to that particular file. It's like data pruning. And this is an old technique that people actually use. So those are the auxiliary data structures you can associate. And that gives you the ability to read in cold data at a very high performance. And lastly, the vectorized execution engines that take advantage of the modern CPU with SIMD in a single instruction, multiple data. So you can actually have this vectorized execution happening in parallel. And one of the things that we actually did at Databricks level, Delta Lake engine, we actually saw an enormous performance gains when we compared using these vectorized engine and using these technologies against some of the cloud competitive offerings available possible. And we were fairly competitive. You know, we weren't better than that, but we were actually close, using some of the major TPC benchmarks for doing SQL queries. And so this is the second bit that actually undergirds the lakehouse vision, and that allows data scientists and ML engineers to be able to deal with large amounts of data, which is an important part of doing your task. And the last bit about how these undergird themselves is the optimized access directly using data science and ML frameworks. And today, most of the machine learning frameworks that I talked about have the ability to directly read Parquet files or org files or whatever files they actually have in the data lake. And they also provide declarative interfaces so that I/O can be enabled for further optimization. So for example, if you look at the Spark data frame API, you can actually use its domain-specific relational operators, which translates internally into a query plan with relational algebra. And then the query plan can then be further optimized by the query engine to say, okay, I'm going to push it down to the Delta Lake to give me the exact files that I need. I know exactly where the indexes are. I know where the data resides, and I'll bring back my training set that you have asked for. And now you actually get this in a very efficient manner. So these underlying confluence of emerging technologies are really what I would say the three legs of the stool, which are actually making the data lakehouse vision possible. And we're beginning to see a lot of noise and a lot of adoption in the ability to actually provide that as a new architecture to handle some of the data problems to look at beyond 2020. And so if you combine those simple architecture with the combination of what you actually expect in terms of performance and transaction from a data warehouse, and use the lakehouse as a simple enterprise data architecture, you begin to see that this is really going to take off, and this is really the future. And the question now is that you can use the Delta Lake, which is now, I'm wearing a shirt, as you can see. You can use the Delta Lake to be able to actually use your storage at a massive scale and use that as part of the data layer on top of it, and then provide the SQL access to that. And for machine learning to be able to do it at scale, you can actually use MLflow, which is the next thing I want to talk about in the amount of time that we have left. So this, just to recap, sort of simplifies some of the data architectures. We're going back to the original, where you have a simple architecture that allows you to have all this application, get the data in a reliable manner and in a good quality manner, and also keep the data fresh. And I think that was an important part. It actually speaks volumes to about what I said earlier, that today's problems are data quality and tardiness, and these is purported to be able to actually address those problems at a scale. The second thing I want to talk about is how MLflow fits into the grand scheme of things. I talked about how Delta Lake plays an important part of it, and now I want to talk about how data scientists and ML engineers can build models at scale and manage models at scale, and then have the entire end-to-end process available at the disposal. Now, those of you who have been working in the industry, and those of you who are going to work shortly after you graduate, or those of you already working, have probably realized or probably have heard that machine learning is complex. And I would contend that the complexity is not so much that the math behind is difficult, although you don't need a PhD in it, but you need some literacy and some statistic and certain advanced calculus to do integrals. It's not that the languages and the frameworks that you use are difficult, because most of these actually have abstracted and given you APIs at a higher level, so you can actually create a class for logistic regression, or you can create a class for decision tree, or you can create a class for linear regression. And they give you default constructors and learning parameters that you can actually create a fairly good model. The problem stems from the fact that the methodology in how you create a model is very different from the methodologies that you and I, or those who are software engineers, are used to it. And just to give you an idea of comparing traditional software versus machine learning, the traditional software, the goal is different. The goal over here in the traditional software is that you are given a particular specification, and you have to create a software deliver your software service for it. And the quality now depends on how many bugs you have and what's your SLA. Whereas if you compare that with machine learning, the goal is slightly different. The goal is the business metric. I want the accuracy, I want the probability, I want constantly, I'm experimenting. It's an iterative process. And the quality of the code, of the quality of your product depends on the data. Data is the center of everything. Not that it doesn't depend on your code, obviously it does, but the data plays an important part of it. And the data changes because you want to be able to make sure that you got the latest and greatest data. And it's an iterative process. You go over and over again. Typically in a software traditional environment, your software stack is limited. You might have one database, you might have a couple of works engines, you might have a few frameworks that you actually support. And the limited environments, you might just do it in the cloud, you might have on-premise. Whereas in the machine learning at scale, you want to take the best of the open source machine learning libraries available. You want to use all of them. It's any or all, and you want to get the latest in the language that you're familiar with, and you want to be able to diversely deploy your machine models in a diverse environment. So these sort of adds to the complexity. And if you look at the traditional continuous way in which actually you build a particular model, there's a data preparation part, where you extract the data, whether you're doing ETL or whatever you're actually doing, or you're putting into Lakehouse, that actually has some tuning associated with it. You might be using Python for that. You might be using Spark. You might be using Pandas. You might use SQL, and you'll have some tuning parameters that you actually want to make sure that you use that. But the important part is when you're building the model and you're iterating of the model, you have to be able to actually tune and track the results of those in a manner so that you know to get the best metric that gave you the best tuning parameters. So that way you have the confidence to say, okay, this particular metric, I'm happy with it. The accuracy is 90.9%, or the probability of this prediction is over 98%. I'm happy with that. And that is contingent on data, and that's contingent on tuning. But all of that has to be done at scale, right? Whether you're doing deployment, whether you're doing getting raw data into your lakehouse, whether you're actually doing tuning, whether you're doing distributed training, all that actually has to be done in the scale. So that's the third problem. The fourth problem with machine learning is that how do you actually take the model that you actually have? So let's say Drew created a particular model, and you say, hey, Jules, here's a particular model, here is taken. How does Drew ensure that what he gives me as a model is the one that I can actually take it and deploy it, and I will have the same results? So model exchange is an important part of it, which is part of all the ML ops best practices. And then finally, we are in the time of GDPR, and governance is important, right? We want to find out how the model was deployed, who approved the model, who did the validation, who tested the model, who deployed, what data was actually used, who approved it, what was the provenance, how did it actually arrange it. So all those aspects have to be incorporated when you're actually building this entire model from inception all the way to production. And so to address these sort of very complex issues, we developed a Databricks called MLflow, which we contributed to Linux Foundation, which is an open source product. And we modularized those in terms of, we want to be able to track things when you're actually running experiments, when you're tuning parameters, when you're building and training the model and calculating your accuracy. You run thousands of experiments, so we want to be able to track that, so we know that the best results will comply with our metric. The second thing I alluded to about, I want to be able to reproduce my runs. And if Drew gave me a particular model, can I package it together and put it on GitHub or put it somewhere else where publicly people can just use that particular project and run it in their environment and produce exactly the same results, right? So Gary can actually take what Drew use that as a product to get the same results that Drew used in order to create that model. And then models component is another way to actually package all this particular model, so you can actually deploy this on these different environments. And then finally, model registry is a central repository where you can put thousands and thousands of model to be able to actually version that, use ML ops to transition them from development to staging and all that. So this whole conglomerate of circle of things is sort of modularized in this thing called open source platform called MLflow. And then we provide you with the libraries which are integrated as part of the MLflow. So you're familiar with Python, you're familiar with R, you're familiar with Java or Scala, you can actually use that. Now for experimentation, there are certain things you want to keep track of. Some things are like parameters and metrics, and we actually have the ability to give you a simple API so you can actually just use those to track that. And the UI gives you the ability to actually go in and track these parameters. And we also try to simplify that by giving you auto logging, whereby you can actually use auto log. So automatically actually gives you all this ability. So this allows you to track experiment at scale. The other thing is actually projects. That I can take a particular project and I can capture all the configs that I need, all the data dependencies that I have, all the code and libraries, and I can use that particular project to execute locally or remotely on any of these remote executions. So that's the way to reproduce that. And the third MLflow component is actually models that allows you to build all these different models in different libraries and be able to actually deploy them in diverse environments. So for example, I can actually have all these different libraries that I actually want to use, and I can create flavors of this particular model, and these models can now be deployed in these respective environments without me understanding the underlying complexity of how it's actually done. So model is a way to actually model flavor or model format is a way to abstract that gives you the ability to actually deploy those in the target environments. And because of these, the ability to actually have these model flavors, I can write the models in any of these particular languages, and I can deploy them in a purely Python environment by just loading that as a Python function and doing my predict at scale. So that's the model bit of it. And then finally, the last bit, which is actually model registry. And model registry is a very central place that allows you to congregate and to manage data. Think of it, model registry, as the Git repository, where you actually, except it's not public, it's within the organization. Because as you scale, right, as you scale, people are going to be building lots of models. So how do you actually find out which is the best version of this model? Who built this particular model, who trained it, how it was trained? Can I actually track some of the documentation associated with this particular models for my provenance? I want to be able to have the history of exactly how the model was done, who reviewed the model and who approved the model. Because if I want to have some sort of a governance, I should be able to say this model was deployed and your loan was rejected. I want to see what were some of the features that made that happen. So you have to have the ability to trace that. And then finally, you want to actually make that part of your continuous integration and continuous development process. And that's an important element in model registry. And so let's just look at where at a very high level, you have a tracking server that actually keeps track of all the entities. And entities, I'm talking about parameters, metrics, artifacts, which are models, files that you actually create. And these are now registered in the model registry. And the model registry now keeps all these different versions of the model. You can have different stages within the model registry, such as staging and production and archive. And downstream, people can actually access your model from the registry to be able to use that downstream for either inferencing or for automated jobs, so you can actually also create a REST service so your models can be deployed. And so the important part about model registry, that it actually gives you the ability to actually have unique models, and then within that particular model, you can actually have different versions of the model. Every time you create a run, you create a different version of the model. You actually have the ability to have multiple versions of the model in the same stage. If you're doing A/B testing, this is a good way for you to be able to do that. It also gives you the ability to have all these different versions of the model, and you exactly know what version was created by whom, where it was deployed, what the current state is. It also gives you the ability to document how the model was created. And then this description is like a way of history who actually worked on it. And more important part is that it gives you the entire API and flow for people who are actually doing end-to-end lifecycle. The developer would actually use this API to register the model. A reviewer would actually fetch that particular model, run some tests to make sure that it passed the metric, and if they're happy with it, they can transition the model to production. And then people who are downstream can actually check out that particular model and make that as part of the downstream automated job array service. And this is an important part of it. We just launched the ability to actually have webhooks. So when something actually transitions from one state to the other one, your CI/CD can actually get the notification, and they can launch a particular job to test your particular model to make sure that it passes certain tests. And if it does, then you can automatically update or promote or demote or add comments. And so you actually have a workflow APIs that can be integrated with your choice of CI/CD tools. And so just to recap, I mean, registry is a central place that allows you to have named registry models. The model registry workflows works very much in today's machine learning ops lifecycle. It provides you APIs that you can actually integrate with your CI/CD, and that gives you the benefit of actually doing things at scale. There are different versioning of the model. It provides you different versioning, so you can actually have more than one version of the model if you're doing A/B testing to be in a particular stage. And model stages have different labels associated with. By default, when you create a model, you get a none stage, but you can always promote it to staging, production, or archived. And as I said, I think CI/CD today is an important part. As it was a part of DevOps 10 years ago, MLOps now is the new thing. And if you don't have a CI/CD as part of it, then you can't really do things in an automated way, and you can't do things at scale. And obviously, model lineage with all the comments and all the approval gives you the provenance of who actually worked on that particular model from the description all the way to the deployment stage. And just to recap, and I think we only have about 10 more minutes left, so I want to make sure that I didn't gloss over things and give you the chance to ask some questions. Is that I talked about earlier that there are data problems which have emerged whereby the existing and the past data architecture that allowed us to do advanced analytics at scale had shortcomings. And one of the things that has actually emerged to address those, especially dealing with tardiness and dealing with scale and dealing with the quality of data, is this new emerging paradigm called Lakehouse. And we begin to see that making a lot of noise in the industry. And we're confident that this is going to be the future where you can actually do with data teams, where I'm including all people who are actually dealing with data. And one of the things that simplifies this data architecture, where Delta Lake is a primary component of that storage layer that provides you the transactionality and the ability to do management at a scale. And then MLflow plays an important role for a data scientist to be able to manage these models and do experiments at scale. Now, the other thing I didn't talk about koalas because we don't have any time is that you can actually use koalas, which is, think of as koala as pandas on acid. You know, I'm wearing a t-shirt that says Spark on acid. You can think about koalas as Spark on acid. And so essentially koalas allows you to do EDA across your entire cluster. Pandas are normally good to do EDA on one machine, but if you use koalas, the APIs are pretty much the same as the pandas, but you're actually doing it in a distributed manner. You can actually do it at scale. And so if you're interested to find out about these emerging technologies I talked about that give you really, really the lift and the momentum to do things at scale, go to this particular URL, delta.io, download, learn about MLflow, and also there is the GitHub for koalas. And if you're suffering from insomnia, I have some good material for you to read. I think I found the last two links very interesting. We don't need data scientists; we need data engineers. I thought that was an interesting bit. And then data science is different now, and I think it's an interesting premise in the article where they talk about why data science is different. And I think one of the reasons why data science is different is because there is an interdependency and interplay between members of the data team, because now you have to work with data engineers to understand exactly how they're actually building the pipelines. So these sort of new hat the data scientists and ML engineers wear is a very cohesive and very, very, very interdependent. And this is where the data teams and as I said earlier, you know, data is the new center of gravity, which is actually pulling data teams together to solve the problems. But at the same time, it also nudges you, it also forces you to think about the emerging architecture. So you're not stuck in the past and you're not stuck in the comfort level of your architecture. You go out and do things. So with that, I think I'm going to end We have 10 minutes. I can take any questions. If you wish to contact me because I can't answer the question, I don't have the answers for it, you can follow me on Twitter, or you can actually join me on LinkedIn and just mention that you were in this particular webinar so I know who you are, and so we can actually have a conversation. So with that, thanks a lot, Drew. I'm ready to take any questions you might have.
Excellent. Thank you, Jules.
Let me stop sharing. Yeah.
So yeah, we want to spend the last few minutes here addressing questions. So if you do have a question, you can either post it in the Q&A tool, you can post it in the chat, or you can even raise your hand and we can enable your mic to ask your question directly. So far, I haven't seen any questions, but
yeah, I think some had a question about this. Yeah, the slides are available. I think Drew and the party included that as a URL. So if you actually go to the particular URL, it's a bit.ly URL that has all the all the slides that you actually saw today, along with the links. It's a PDF version of it, so you can actually look at that.
James Shanahan has a question. Hey, Jimmy.
Hey, Drew. Hey, Jules. Thank you so much. Great talk. I hope we have lots of students online and they're learning tons from this great presentation. So I had a question, and it's kind of like at the frontier of machine learning, and it's about automatic machine learning, auto ML. And I just wanted to see where does auto ML fit into the roadmap for you guys?
Oh, brilliant. I mean, it's a good question. I think AutoML is in its formative stages. There was a lot of hype about what AutoML is. We wanted to say, click this particular button and it will solve all the problems. So I don't think we are there right now. AutoML actually does play an important role, whereby it can actually take, you can select some of the initial steps that you want. Let's say you're actually creating a machine learning model that it's actually a regression. And so you can say, okay, use this particular data set with a couple of API calls, and here are the 5 machine learning libraries that I want you to use. I want you to use scikit-learn, I want you to use XGBoost, I want you to use Spark, and then I want you to use LightBGM, just to give an example. Run that for me, and it will create the best model for you, and then it will give you the results by saying, oh, by the way, I found XGBoost as the best for this particular data set. Here are all the metrics that I created, and I've ordered them in the ascending or descending order of the accuracy. So that's where the AutoML is going in. And as far as where we are in the particular roadmap, yes, I mean, this is something that our customers are asking us, and we are looking into it as to make it part of this larger scheme, where we don't want to give you a complete black box. We want to have low code that you can actually have some visibility in the algorithm that you actually choose and the results that you actually want, and it does that for you. But yeah, it is like a part of the AutoML. And I think one great tool that exists out there, which actually is integrated with MLflow, called PyCaret, PyCaret. Look at PyCaret, and PyCaret has the ability with low level that actually allows you to choose the classical machine learning algorithms that you actually want. It will run for you. It will log in all the experiments on MLflow and then give you the summary of, oh, here are 5 algorithms that I used, and here are the metrics available.
Okay, great. I mean, I have another question if there's time. I don't want to bogart the mic here too much. Drew,
go for it, Jimmy.
Yeah, in kind of, again, similar spirit, on the frontier again, federated learning. And I just wanted to hear your thoughts on federated learning. Maybe it's a bit out of scope here for what you're doing, but maybe it's also on the future roadmap. And in that vein, we talk about ethics and kind of like curating data and controlling access and so.
Good. I mean, the question about ethics and federated learning and distributed learning all sort of come into how do you once you give your particular data, and do you actually, when you prepare the data or when you examine the data, are you looking for any biases? Are you looking for any things that might be ethical? Or when you're actually making a decision whether a certain person can pass a health test, or a certain person can get a coronavirus vaccine, or a certain person loan is approved, what were the criteria and what were the features you actually use? So I think part of that is what we call the interpretability of the model, right? And we in Databricks, as part of the MLflow, we were provided for you to create SHAP, and gives you the importance of what particular those features are, so you can actually look at how this particular model evaluated your decision based on the importance of the features. So that is part of the ethics. And I think the other question about distributed learning was, yes, you can actually do distributed learning. You could use federated learning today on Databricks by using Spark with hyperparameter, or you can use Spark trials. And I think there was another question that says, what are some of the particular features you see with this data at scale in healthcare? I think healthcare is an important industry. I think we have created this thing called genome project called GLOW, which is the open source project that allows you to be able to deal with the scale of genomic analysis, right? And when you're dealing with that aspect of how do you actually deal with that, Regeneron is one of the companies or customers who are actually using that to discover drugs by understanding the genome. And so that is one industry where it's actually playing a huge role in the health industry.
Yeah, thanks for that comment. I've also noticed that there's been a lot of talk about doing personalized N of one in the healthcare space, where you can look at your own personal data. That also has a scale attached to it, like Apple looking at all the watches and all the data they get from watches. What kinds of things do you think you can do, or one could do in that space?
I mean, the data governance, I mean, the ability to actually filter the data is something that has to be sort of worked out as a policy, right? It is something that data collectors and data curators are constantly dealing with. What kind of data we should collect, and how we should actually expose those data. So I think those are the questions which are going back to the ethical question, how you actually deal with that. But in terms of having tools, I mean, the tools are going to be no different, right? Once you get the data, how you anonymize it and how you keep it. And this comes into healthcare data where, what data, when you present it, are you taking the PIA data and you're actually taking the right precautions to make sure that when you present the data, whether those are graphs or whether those are analytics or whether features, you are anonymizing it so you're not compromising the data. So those are part of the data preparation and data presentation tools. I mean, those are sort of all technologies people use, anonymizing data, making sure that we comply to all the HIPAA acts. And so all that obviously Databricks is very, very, very much cognizant of it, and our vertical industry, especially healthcare, does ensure that whenever we store a particular data, it is in your cloud, it is secured, it is anonymized, it is encrypted, whatever things you actually want to make sure. Yes, you have to be paranoid about those things.
Yeah, I think it's interesting that maybe healthcare will be one of the early places to have different levels of anonymization.
Yes.
And so that kind of goes into the whole layering, the management layer in your data lakes.
Yes. So the management layer is really, that's where it actually comes into place, because now you want to have control over the management layer, right? So the management layer can say, okay, Drew can only look at this particular data, these files, and James can only look at this files, or Fred can look at all the files and encrypt and decrypt that particular data. So the access layer of role-based access control is part of this management features, right? So when an application says, give me a particular table, and that table has a sensitive data, I need to be able to say, no, Drew is not allowed. Drew is requesting for this. He can't look at this particular column, and he can't look at this column, even though I might present that particular data, but it's going to be completely anonymized, and he can't make sense out of what that particular data is. Whereas if Fred accessed that particular data, and he has access to be able to look at all the rows and all the columns, because he has been given the role-based access control to change those things, those are part of the management layer. And this is where the Delta Lake actually comes in. And so we are working to ensure that role-based access control is part and parcel of your access to that particular management layer. And this is all part of the management meta layer.
Yeah, thanks. I've got a follow-up question, unless someone else has something they want to ask.
There are a few other questions, but we can take it, Fred.
I just wanted to follow up and say, what are maybe some kinds of things you see for the future for healthcare space in terms of maybe the size of data that we're going to start seeing, and what kind of things we'll see in the future?
Yeah, I mean, the size is an important part, right? And I alluded to one of the things where we're actually building this thing called Glow that Regeneron actually uses to be able to have terabytes of data to analyze drug discovery. So I think this is where the scale of the data is going to be. The scale of the data is going to be in this space where healthcare is exploding, and especially if you're doing genomic analysis, that's where the scale comes into play. And so we are building pipelines along with our healthcare industry customers to say, Regeneron is one example. How do you actually deal with this massive amount of data? And if you get a chance, just look at the project called Glow. It's an open source GitHub repository called GLOW. Like I said, we have all these particular tools, and I can't really cover everything in 45 minutes, but I can give you pointers to that.
So Samid has a question in the chat. It says, a lot of companies have adopted the Snowflake data warehouse, even over AWS Redshift, with ETLs for their data needs so far, given the scalability and performance for querying data. So when do you think Lakehouse Vision will allow data lakes to be queried in a similar fashion? I
mean, you can actually query today your Lakehouse, and we're already beginning to see some of our customers are moving from Delta Lake using Lakehouse. And given that we actually have built this Delta engine as a layer that gives you fast performance, you can actually do that today. So if you're on a Databricks today and you want to enable Lakehouse and you want to enable Delta Lake and you want to use the Delta engine, you can actually do that. Now, right now, all that is in private previews. Once we make it available, that will be something that customers can actually use it. But to answer your question, the whole reason behind Lakehouse is that you want to take the best of the both worlds, whereby you can actually do your SQL queries the way you would expect that you would do in a high performance relational database, but do it on a data lake storage. And that's where the management layer comes in, and that's where the Delta Lake storage comes in, and that's where the SQL engine that we have built and we ran some benchmarks against some competing data warehouses to look at some of the queries. And so, yeah, you can actually do that today. And like I said, this is something that's going to happen, and it's just a matter of time before we see the Lakehouse. If you go to any of the big vendors, you will actually see them mentioning aspects of the Lakehouse.
John's asking, can Delta Lake sell the insights found in data to other companies?
Well, Delta Lake is a storage mechanism, right? Whether you actually want to sell your insights, it's up to you. Whether you're ethical enough to sell it, it's not up to us, right? Because the data is going to be stored in your account, and it is secured. But if you take this particular data and sell it to the advertisers, I don't think we are in the police mechanism to say you can't really sell. We are giving you the enabling technologies to be able to process the data at scale. And what you do with the insights and what you do with what you actually garnered and what you discovered is up to you. Now, whether it's ethical of you to actually sell that data is up to you. Whether you're actually doing it for good cause, be all the power to you. Whether you're actually doing it for nefarious reasons, may you go to jail.
Oh, and to be clear, I think maybe just inferring that they were speaking of, would Databricks do this?
Oh, no. I mean, I can say, I don't think we are in the business of selling data, right? Because we are providing managed services for you to process the data at scale. And we don't tell you exactly what you do with data. We will give you the ability to secure your data. We'll give you the ability to manage your data. You will give the ability to anonymize and make sure that the right people who have access to your particular data in the data lake. But then after that, what you do with the data, if you publish it on a website, we can't really do much about it.
Great, thanks. Sohag asks, can you speak to how MLflow can be incorporated into a typical software development lifecycle from a CI/CD perspective? And in particular, how to synchronize the models, the ML models, and the application software used to deliver the results of the predictive analytics to customers?
Okay, good question. I think because of the time constraint, I sort of glossed over quickly how the model registry workflow is an important part of MLOps. Today, the model registry has workflow of APIs that allow you to transition model from one stage to the other one. And we have introduced this whole notion of notifications. So let's say, for example, I have a particular model that I registered, and Drew is the chief data scientist, and he says, Jules, you have created this model. I got a notification saying the model is in staging. I'm going to run some tests. So Drew can actually now enable or automatically have some jobs that actually run to test with some validation data. And if the validation data passes, then Drew will make a decision that I'm going to go ahead and update the model to production. So when he updates the model to production, now it creates another stage in the webhook. It's another process in the CI/CD. Now I'm deploying in production. So the MLOps people says, oh, this particular model that actually predicts a certain data is now ready for production. I'm ready to actually now deploy it. And now you can deploy it in your REST serving as a service, or in a Kubernetes cluster, or within the Databricks. We actually provide you a way to deploy that automatically. And so now you can actually build that as part of your application. And then what you do with the results is whether you can actually take those results and either display them in a tabular way, or you can put that back into data lake where it said this model ran for batch inferencing for this large amount of data. These are all the results that are played, and you can actually create dashboards and all that. So there are various ways you can actually use the outcome of that particular model inference, whether you're doing in real-time inference or whether you're doing batch inference, and that would be sort of one way to use the results of the deployed model. Another use case, just to build on top of that, suppose you're doing model drift and model monitoring. That's an important part of it, because remember I made the claim that data changes and you have to change your model based on data, because now your model might drift. There is the concept of data drift and data monitoring. How do you do that? One way to do that, you constantly monitor by validating the data to see your accuracy is not drifting over. And once it starts drifting over, you know your data has actually changed. So it's time to read this particular model. So one thing you can actually do is provide notification as part of CI/CD. Hey, this model is actually drifted. We need to take it out of production, or have another model that starts training with this new data. So now we actually we mitigate the data drift. So that's all part of the CI/CD. And we provide you APIs to integrate with whatever you're using, Jenkins or GitOps or CI/CD. Webhooks are the way for you to actually say, here's a trigger that I want to be associated with this particular event. And then when that event happens, we enable that trigger. And that trigger could be just a REST call to your CI/CD to create a job to run it. Or it could be, send a text Slack message to my grandma to say, go flush your toilet.
Jules, so one more question, one last one.
Yes.
Given the size of data is ever growing, what are some of the techniques to push some of the processing logic to the edge? Do we need to bring all the data to one logical location? Or are there processing that can be pushed to the edge so that the amount of data that needs to come to a central location can be reduced?
I mean, good question. I think, doing inferencing in the edge is an important part of it, especially if you are, say, working in oil rigs in the middle of North Sea, or if you are somewhere in the Pacific Ocean, and we have this small devices that are actually detecting sensors which are battery driven or solar driven, that cannot really store all the data, but they have micro models which are part of that particular embedded in the ARM chip, but they can actually do inference right away. So they look at the particular sensor data, and if the data says, hey, this is something that's going to happen, I'm going to call the mothership. So you can actually do the edge detection, or you can actually do the edge inference by deploying this model at this particular ACES. But then every now and then, when the data is actually collected, when it's reached a saturation, you can upload the data to the central place, so it can actually be used to do the training, and then you can deploy the new model back to the edge. And that actually happens. TensorFlow Tiny allows you to do that. All these other micro devices have models built into it that I can actually do inference at the edge. I mean, object detection is great. For example, animal conservationists in say in Africa, in Serengeti Park or in Mara National Park have deployed these object detection cameras to detect coyotes and to detect poachers and to detect all these things. And as soon as they actually see that, they do that. But the model is not trained on that particular micro device. The micro device is very low powered. It doesn't have the computer, but it has enough compute resources to be able to do the inference. But the training is done elsewhere. And then the model is deployed on this particular devices, which are solar powered, and they have enough battery to do the inference and detect that.
Excellent. Well, thank you so much, Jules, for this presentation,
You're
for walking
welcome.
us through MLflow and Delta Lake, and for sharing all this knowledge with us.
Well, it was a
It's been
pleasure.
great.
It was a pleasure. It was a pleasure. I'm always love to share whatever I can.
Excellent. Thanks so much. I also want to thank Databricks for hosting this entire lecture series. It's really been a great experience for myself and for the iSchool community. And I really do look forward to further collaborations with the good folks at Databricks. I also want to say thanks to Tia Foss and to Rob Reed for organizing the series, and to Gary Morphy-Lum for his great tech support throughout. And finally, thanks to everybody who joined us today. Yes, the recording of the presentation is going to be posted on the events page of the iSchool in the next week or so, as soon as we get the transcription done. Again, thank you so much. Thanks, Jules. Take care, everybody. Have a great evening.
All right. Good night and be safe. Cheers.